Self-induction. Self-induction. And it says that the electromotive force, basically we know it starts with the notion or the proposition that E is equal to N delta phi by delta T. Okay, this is the first thing. Okay. So basically this phi is phi B. Yes, so it's getting a little tricky, but we will not leave it like this. So okay, we have this proposition that let's say N phi is directly proportional to, no wait, from here we can establish that E it's already established that E is directly proportional to N delta phi B. Let's just call it delta phi for simplicity by delta T. Okay, and we have the constant of proportionality here, which is removed. We remove this constant of proportionality to get the proportion from the equation. Yes, so it means that K is equal to 1 in Si, for example. Yes, so phi is also basically directly proportional to current, actually delta phi in this case. The more the change in magnetic field, the more the current we have. Okay, so what I will do here is, for example, we have a situation which says phi is directly proportional to I. Yes, delta phi, the change in magnetic flux. Okay, it's directly proportional to the current. So E is directly proportional to N I by the change in current. Actually, the change in field is directly proportional to change in current, and then in the above proportion, delta I by delta T times N is proportional to E. Yes. Okay, so So it's not difficult, and we know that n is the number of turns. Yes, so n is the number of turns, and n can be constant. So let's say n can be approximated as a constant in this situation. So E becomes constant times rate of change of electric current with respect to time. Yes, delta I by delta t. Yes, so this is the form we have. But since now we have this thing here, and I tell you what, that the number of turns can be approximated to length, because the more the turns in the coil, the more the length. Yes, so we have another way of writing this form, which says length, or differential length maybe. Okay, differential length okay, length, let's say length, and the same thing repeated, delta I by delta t here. And after that, what we do is we take an approximation. It says that L delta I is roughly equal to delta Li. Yes, change in current times length is equal to both change in change roughly equal to change in length times current, or both let's say change in length times current, the differential of the both. But here it's slightly different. We will use whichever gets us to the next convenient form for the application. Okay, so for unit cases, n can be 1 and n is equal to L will be 1. So this form might just get into, if I'm not wrong, delta I by delta t. Yes, the rate of change of current with respect to time, approximately in the unit form. I'm not a scientist, but these approximations do work in some situations. So now, mutually induced electromotive force. It's not very different from the previous work. Mutually induced electromotive force. Yes, and it says what? Starts with the same notion, very similar one. E is equal to n delta phi by delta t. From here we assume that delta phi is used for the change in magnetic flux. The subscript B will also be put and sometimes also not. So okay, you see, so there's a bit of a drama here, but it's sometimes required, as I indicated earlier. So there's a bit of a trick here, and it's E is equal to delta n phi by delta t. Now first the change in flux and then the change in number of turns. You see, as n delta phi is roughly equal to phi n delta n phi. Okay, and delta phi is roughly equal to delta n phi. So this is change this, and then we know that E is this makes it into k delta I by delta t. Yes, and k is the constant here, so we use k as a constant, and it says what? It says E is directly proportional to delta I by delta t. Okay, but we don't work too much with the proportions, we work with the equations. So what happens is we get back to our equation. E is equal to k delta I by delta t. Yes, this is what we get back to, and now we use m instead of k. K is approximately equal to m, which is the collection of constants. Yes, so what we do is E is equal to m delta I by delta t. Okay, this is what we do. And now one more approximation, and that m delta I is roughly equal to delta m I. Change of current into this constant m is roughly equal to change in the collection of constants, which is m, in this case delta m times I, the current. Okay, so we get the form delta m I by delta t. There are too many approximations in electricity and magnetism as compared to, if compared to mechanics, because mechanics seems quite obvious, but there's there are of course parallel aspects, but then there are differences and slightly changed approaches, different methods, let's say. Induced electromotive force, I want to discuss this because there's a difference between mutually induced and induced electromotive forces. Yes, so we will get to induced electromotive force. Yes, so we start off with the magnetic flux here. Phi b is equal to phi is equal to b dot a phi is equal to b a cos theta, yes, and theta is equal to omega t. All right, omega is equal to theta by t, so theta is equal to omega t, so we make the substitution. Phi is equal to b a cos omega t. Yes, so this is one and this is the substitution, equation one, the substitution one, and then we put them together. In the electromotive forces, with the sign convention, minus n times delta phi by delta t. Okay, this is it. Now we put the value that the form of phi is equal to minus n b a cos omega t by delta t is equal to minus nab delta delta cos omega t minus nab delta cos omega t by delta t. Okay, and E is equal to minus nab delta cos omega t by delta t, and cos omega t is equal to minus omega sine omega t. You see, here's the trick. So if limit delta t approaches 0, that's the condition, so cos omega t will be equal to minus sine omega t. So we use this substitution, so E would be yeah, means that when angle approaches 0 degrees, wait, the situation is that we have now sigma is equal to minus nab sine omega t. Delta t approaches 0, so delta cos omega t by delta t approaches minus sine omega t. So minus minus gives us plus, so this sign gets removed. So we have E is equal to nab sine omega t. And also we know from mechanics that sine, okay, omega is equal to 2 pi by t, which makes it equal to 2 pi f. Yes, we can use either. E becomes nab sine two pi by t, and t cancels with t, so sine 2 pi. Okay, 2 pi by t, and 2 pi f 2, 2 pi by t dot t um, says 1 by t is equal to f. So there's one more form we can establish, NAB sine 2 pi f t, frequency into time. Yes, so these are basically the equations. 2, 3. Yes, which can both be used. It's just a little bit more we can do here, and we know that sigma max in this situation will be equal to NAB, because sine the collective angle will be 1. So this implies that sigma will be equal to sigma max times sine 2 pi t by t. Yes, so this becomes an equation of interest. So we discussed the case of a transformer, and it is used for either stepping the voltage up or stepping the voltage down. So we have the form. The general one says that the voltage is equal to number of turns into delta phi by delta t. Time rate of change of magnetic flux uh, times n gives us the voltage. Yes, for the let's say for the primary voltage we have the number of turns in the primary coils into delta phi by delta t, and then the secondary voltage, number of turns in the secondary set of coils, delta phi by delta t. This is 1, this is 2. You see, so equation 2 divided by equation 1 now, which means Vs by Vp is equal to Ns by Np dot delta phi by delta t dot uh, delta phi by delta t. So this term gets cancelled out, so we get Vs by Vp is equal to Ns by Np. The ratio of the voltages in the secondary and the primary section is equal to the ratio of the number of turns of the coils in each set, secondary to primary. Yes, this is the form we're looking for in a transformer. And P is equal to IV, we know, and P out is equal to Pn. We know from the basics of electricity that P is equal to IV and P out is roughly equal to P in the system. Yes, There are some losses, practically 20%, but we can approximate. So out is in the secondary set, so ISVS can be equated to IPVP, the product of current and voltage in the secondary set to that in the primary set. Okay, this gives us Vs by Vp is equal to Ip by Is. Now things change a little bit because now we have it reciprocated. The ratio of the current in the primary to the secondary is equal to the ratio of the voltages in the secondary to the primary. Yes, so this is 4 here, and you see, as we know that Vs by Vp is equal to Ns by Np. So Ns by Np becomes Ip by Is too, because Vs by Vp is also equal to Ip by Is. Yes, subscript Ip by Is. So we can rearrange and develop another form. Number of coils in the secondary section to the current in the secondary section is equal to number of coils in the primary section to the current in the primary section. So this can very much be used in situations of application, and I do not want to get into alternating current because that's a little bit tiring, at least not today. After tonight we'll see about the alternating current. Electromagnetic force and power with respect to electromagnetic force and electromotive force uh, in a circuit where the circuit has a resistance R and battery with a small resistance R as well, and current I. So the electromotive force basically can be approximated to the terminal or functional voltage, and